C1 to C2,
那行，
to C3,
还好听得懂这边。
or C4, and differentiate it for acceleration to C2, 6C3, 12C4. So those are my 9 sets of equations for each of the segments for this 4, 3, 4 trajectory. So if I were to do a sketch, that acceleration, and that constant velocity, I'm not going to draw a straight line, but any kind of line, and then deceleration. So you have 3 segments. Segment 1, segment 2, segment 3. Why is it not a straight line? That's because for your second segment, you could already see that it's a third order. It's not a first order. So it's part of that third order curve. Same as your first segment. Your first segment is part of the fourth order curve. Or your third segment is part of the fourth order curve as well. Out of these 3 segments, there will be initial and final position. So second segment is initial, final segment. Third segment is initial and final segment. This is time. So this will be, at that point of time, there will be my T1F. That is my first buyer point. This one over here, my second buyer point.
为什么它的这个这样子的状况不是直线的，全部是刻画？是吗？
And then that one over there is my third buyer
Third 跟 fourth
point.
order
acceleration. 应该是 second order, first order.
哦，那这是 first order。
That one over here, T2F, the final time of your second segment, T2F. This one over here, the final time of my third segment. So let me outline all the boundary conditions, 14 of them. The first one is when T1F, T1I, T1I at 0 seconds.
Always ask question.
So I'm going to have theta 1 at 0 seconds equal to A0. How I get A0? That's by just substituting 0 to all this time over here, for my t equal to 0 time. So I get an A0 over there. Second boundary condition, riding on that, my velocity at that initial position will be equal to substituting 0 over here, you get A1. The third boundary condition, also substituting when time equals 0 to my acceleration over here in the first segment initial position.
这个是什么
That's equal to
？T1I 还是
A2.
T1F？
那个这个，
就是下面那个
对啊 ，OK， 那个是 D1
T1I。
And between this final point of first segment to the initial point of your second segment, they must be equal to each other. So what that means is that it will get me my fourth boundary condition, which is theta 2I. I think your notes is written as just theta 2, but I think theta 2I makes it clear that this is on the theta second segment initial part. This one must be equal to theta 1 at the final T1F time. So what that means is that this will be equal to A0 plus A1 T1F plus a2 t1f squared plus a3 t1f cubed plus a4 t1f to the power 4 for the fourth order polynomial. So you could see that as you write, if you don't have a steady mind, you may write like a TF. You will lose some marks. You will lose some marks if you write as TF instead of T1F. Because that TF, it can be any of this. These are all the final points. But which segment is it? The fifth boundary condition will be that the first buyer point must be the same as the third order segment initial position at t2 equal to 0. What that means is that t2I, we let it equal to 0. What it's trying to do is to relate this segment over here to do the projection until it reaches 0 at the time 0, so as to draw the entire curve of this third order segment. So this is fourth order, this is third order, and this is fourth order. Why do we need to take time at 2 to be equal to 0? That's because then we have a point of reference. So we start the sketch of this third order curve, starts it at time equal to 0. And then we just take the segment that we want. So time 2I equal to 0. If that's the case, then your theta 2, if you substitute time equal to 0, that will be equal to d0. For your sixth boundary condition, you need velocity continuity. For velocity continuity, that means your theta dot 2 at time equal to 0 must be equal to theta dot 1 at time 1f. What that means is that this point over here, the velocity at the final point of segment 1 must be equal to velocity over at the final initial part of your segment 2. So these two must match your velocity. This is what this is saying. And if that's the case, if you substitute 0 into your velocity of your second segment, you get it to be v1. Substitute t1 into your first segment, t1f into your first segment, you get a1 plus 2a2 t1f plus 3a3 t1f squared plus 4a4 t1f cubed. Seventh boundary condition. We look at your acceleration continuity. A lot of years this question always come out. Don't know why. Maybe because you need to write a lot. So here dot 2
对啊，我懂为什么3个小时呀？
因为这个
at time equal to 0 must be equal to here dot 1 at time 1f. Right, so that's why we can have a good length. The acceleration also must match so that you can get a matching transition. So if you substitute 0 into the acceleration for segment 2, you get 2d2. I'm not going to work it out. You can work it out by substituting 0 into the acceleration equation. So for acceleration equation for segment 1, substitute T1F into it. So you get 2a2 plus 6a3 T1F plus 12 a4 T1F squared. Eighth boundary condition. The eighth one says, very similar to this fifth one, it says that your second buyer point or buyer position must be the same as your fourth order segment, which is your deceleration phase, that initial position at time 3 equal to 0. So why again time equal to 0? That's because, I'll go back again. That's because this part here, your fourth order, we take it to be this curve, it goes something like that or whatever, and ends up at time equal to 0. We don't know how it's going to look like for that fourth order equation. But that fourth order equation, we're going to just take that small little part of it and then try to find it out using this initial condition of time equal to 0. So that's why you have time t equal to t3 equal to 0. So if we have that, so t3i equal to 0 seconds, so your theta 3 will be equal to c0 because all time will be equal to 0, so you just get c0. Ninth boundary condition. Ninth boundary condition, we need to say that your theta 3i is equal to theta 2 t2f. Right, so that initial position of your segment 3 must be equal to the final position of your segment 2. So what that means is that you get this equal to b0 plus b1 t2f plus b2 t2f squared plus b3 t2f cubed. The next boundary condition, again, is about velocity continuity. You have theta dot 3 at time equal to 0. This one must be equal to theta dot 2 at t2f. If you write t1f over here, then you lose some out because we are talking between segment 3 and segment 2. So for that, velocity of your third segment, substituting 0 into that equation, velocity equation, you get c1. Substituting t2f, you get b1 plus 2 b2 t2f plus 3 b3 t2f squared. 11th boundary condition is about acceleration continuity. So for that, we want the acceleration of the third segment must be equal to the acceleration of your second segment at time 2tf. So substituting 0 into your acceleration for your third segment, you get 2c2. Substituting t2f into the acceleration of your second segment, you get 2b2 plus 6b3 t2f. 12 boundary condition. 12 boundary condition says that your theta 4i equal to theta 3 t3f. So if you're wondering, where's 4i coming from? I've only got 3 segments. That's because we try to relate that ending part, right? I'll come back to it. We're trying to relate this ending part with another order equation, correct? Connecting it. This one, we don't know which order is it, but we call this as my fourth segment. The fourth segment. So the fourth segment over here,
太多了，
the initial point will match with the final point of your third segment.
拿不到，拿不到，
So that's why we're going to use 4.
我真的这样。
So for this one, we do not need to know what is the position of the fourth segment. But for my third segment, T3F, will be equal to C0 plus C1 T3F plus C2 T3F squared plus C3 T3F cubed plus C4 T3F to the power 13th boundary condition relates to this velocity of that final point. That is, 0.4 must be equal to 0.3 T3F. So that will give us C1 plus 2C2 T3F plus 3C3 T3F plus 4C4 T3F cubed. The last boundary condition, acceleration of that final point. The acceleration of that is equal to the third segment T3F. So that will get us to 2C2 plus 6C3 T3F plus 12C4 T3F squared. So you'll find that although your notes kind of gave you all of that, but I kind of insert a little bit of my own. So you can choose to write that or just leave by your notes as well. So now that we have 14 boundary conditions, that's where the fun time starts. To solve for all the 14 unknown coefficients. But then you'll be wondering how to do that. And you're asking, Dr. Tan, serious? You want me to do this in the exam?
Yes.
How many hours are you giving me?
3.
Yeah. So you only got 3 hours, you got other questions to do, so I don't think you will get a question that asks you to solve 14 coefficients, right?
No, we're going to get it.
But you need to know something. How can we solve
Say everything.
without solving them? How can we put it together so that it's easy to solve? So this is what
这
you
个
need
写
to
下
do.
来也是个问题啊。
不一样啊，我好懂。
What we need to do is to put all these 14 boundary conditions into a matrix. A huge matrix, a 14 by 14 matrix. This 14 by 14 matrix would have theta, capital letter, equal to that M matrix multiplied by the C matrix.
好感，
What are all these?
什么来着？这样因为那个 capital，
This C matrix,
什么叫 matrix？
it's written here. This C matrix is equal to all your coefficients. So if you look
要
at
找一个，要找一
the
个
equations that are wrote just now for position, for that first segment, there are 1, 2, 3, 4, 5 coefficients. Second segment, there's 1, 2, 3, 4 coefficients. Third segment, 1, 2, 3, 4, 5 coefficients. So putting all these coefficients together, and I call it a C matrix, a coefficient factor. A coefficient factor. So that coefficient factor is going to look like this, with this to the power of T. It's called transpose. So transposing means that you convert that one row into one column, transpose it. Right? You learned about this before, right? I don't shake your head. I know you learned it before. I saw you post. You know about transpose. And the theta vector also again is going to be holding up your theta 1. This one will be your theta 1 dot. This theta 1 dot dot. And theta 2. All these things, where did it come from? It came from all our 14 boundary conditions. So if you look at your 14 boundary conditions, starting from the first one, we were talking about theta 1. Second one, we were talking about theta dot 1. Third one, we were talking about theta dot dot 1. And etc. in a whole way. So that will form your
我要放这个
theta matrix.
我拿掉那个 transpose 它就变成
So now left with this M matrix. How do we formulate the M matrix?
哇，很漂亮耶！
I've created this array, although it's written over here, I'm tempted to say deal with it, go and find it out. I'll walk you through. Okay.
Sure not.
Okay, what's the first boundary condition? Can you read it out just now? First boundary condition? That one was
0.
theta 1 equal to A naught, right? Theta 1 equal to A naught. So I'm going to form that M matrix. So that M matrix, how do we write it down for that just one line of A naught? Knowing that there is this A naught at the C matrix already. So what's happened is that this is your M matrix. You have your theta matrix. Maybe theta, I'll write it over here. So your theta matrix, I'm going to write it down based on this. You have theta 1, theta dot 1, theta dot dot 1. Next one, theta 2, theta 2, 0, 0, theta 3, theta 3, 0, 0, theta 4, theta dot 4, theta dot dot 4. This is your theta matrix transpose equal to your M matrix. M matrix is going to be here, and then multiplied by your C matrix. So in C matrix will be A0, A1, A2, A3, A4, A0, B1, B2, B3, C1, C1, C2, C3, C4. That is your C matrix. So in order to get the first equation correct, which is theta 1 equal to A0, what that means is that this one must be 1 and subsequently zeros, right? That will give you your first boundary condition. What is your second boundary condition? Second boundary condition is A. Second boundary condition is actually theta dot 1 equal to A1. Right? So in order to formulate your M matrix over here, that would be 0, 1, 0, 0, 0, and everything else. Right? That will form your second boundary condition. The third boundary condition, that is your theta dot dot 1 equal to A2. To A2, right? So what you need is 0, 0, to A2, and then the rest 0. And you will go on. I think it's exciting to look at the fourth one. The fourth boundary condition. If you look at your fourth boundary condition, I'll just read it off to you. Fourth boundary condition is theta 1 equal to A0 plus A1 T1F plus plus A2 T1F squared, A3 T1F cubed, A4 T1F to the power 4. So you have A1, which means this part here will be 1, followed by T1F, T1F squared, T1F cubed, T1F to the power 4, and 0, 0, 0 for the rest of it. Alright, that will give you your fourth boundary. So I'm not going to work through everything, but I want you to look for your seventh boundary condition, because that one is a bit tricky. So if you look at your seventh boundary condition and just fill in this seventh line over here.
Okay.
Just by yourself, look at it, that seventh line. I'll give you some time. Just write that out, and then later on I'll write it out and see does it match. Seventh boundary condition relates to acceleration. I'll write down that boundary condition. How to write down these boundary conditions into your M matrix? The way to do this is that you must move this to the right hand side. So 2A2 plus 6A3 T1F plus 12A4 T1F squared minus 2B2. Then you can formulate your M matrix, because now your theta is equal to 0. That's why you have this 0. So I just fill in that line, and then you could have a check. Have you gotten it right? So this will be 0, 0. That will be 2 because of 2, 8. 6 T1F, 12 T1F squared, and then 0, 0. And you have this minus 2B2. So you get this as minus 2. And then the rest will be 0. So if you form all that M matrix, you get this bulk here over here. Your subsequent robotics lectures, you do a lot with this kind of size of matrix, and so you can start to get very comfortable with this size, this kind of size of matrix. But why do we have this matrix? That's because at the end of the day, we want to find out how do we go about solving for our coefficients, these C coefficients. So in order for us to be able to solve for our coefficients, what we need to do is that we express C that's equal to theta multiplied by the inverse matrix of M. Right? The inverse matrix of M is huge now. It's a 14 by 14 size. So inverse of that requires non-human power. That is your computer power. Okay, so I don't think you're even a computer in your exam. So I just need a little bit more time to wrap up with an example. So in this example, you would have all your conditions given to you. So I'll just use a different color marker. In that example, You're given this theta 1 equal to 30 degrees, this one is 0, this one is 0, theta 2 is 50 degrees, theta 2 is 50 degrees, 0, 0, theta 3 is 90 degrees, and your theta 4 is 70 degrees, and then the velocity and acceleration condition you're given as 0, 0. So in there you're given what is T1 value. Your T1 is actually 2 seconds. So you'll be filling in over here 2 squared, 2 to the power 3, 2 to the power 4 in order to solve for matrix. So doing all that, so T1 is 2 seconds and it's squared over here. So if you do all that, we can actually find out what is that final C factor. So without going to that sort of detail, eventually you're going to get all your coefficients. Your coefficients A0, A1, A2, A3, A4, coefficients of B, coefficients of C. What is important is this next graph over here. After you've gotten your coefficients, that means you would have your equations for all your positions. Wait, yeah, just hang on a bit here. That pain is going to be quick. We're going to finish. So these are all your 3 equations for your positions. Right? With all these 3 equations, then we can plot out that graph. So you will have your first section and your second section, and then your third section. First, second, third section. In a 4, 3, 4 trajectory. Actually at 2 seconds. So here is your first segment. Your second segment is going to be here. Okay? This is your second segment. Third segment is going to be over here. So now the critical question is this. Just now we saw this thing about acceleration. It has this drop, right? Just now we were talking about acceleration was 10, and it dropped to 0, and it dropped to negative 10. In this case, you could clearly see the acceleration profile as that. This way, and then that way. Now the big question now is, do you think you're going to experience jerkiness? Nope. How do I define then jerkiness? If there's a sudden drop, yes, I experience jerkiness. This one, it seems like you have the acceleration that's moving upward, downward. It's upward and downward, it's still acceleration. Yeah? It's only when it goes to negative that it's deceleration. So over here is still acceleration, even though it's coming down over here. It's just lower acceleration. And then you have a constant drop in your acceleration going into deceleration. Deceleration, slowly, you kind of like, it's not that much deceleration, going into positive acceleration. And then still positive acceleration, but a smaller value. This point over here, do you think you'll experience jerking? The answer is actually no. It's only when you have a sudden drop, then you experience jerkiness. But if your acceleration, even though it doesn't move smoothly over, but it moves a joint together to the next acceleration profile, you will not experience jerkiness. So this kind of 4-3-4 trajectory is good. It's good for this smooth profile of moving your robotic arm through. So with that, my segment comes to an end. Talk a little. We some chance. I'll next see you over at the robotics competition. Today's Wednesday. Yeah, every Wednesday afternoon you go for next Wednesday afternoon for 4 sessions. You go for your robotics lab. It's a tank climbing. It's going to be your lab supervisor. He'll be teaching you how to go about doing your robotics construction. Please give your robot a name here. And this year, we plan to keep one of the robot that we feel can be used to entice your juniors or to bring it to the open house.